All right, so let's start the problem solving for chapter number 13. Okay, so let's start with question number 1. So here we are given the room temperature, and room temperature is normally 20 degrees Celsius. Okay, and now we have to calculate the room temperature in degree Fahrenheit and also in Kelvin. Okay, so how to solve this? So the equation we need is this equation. For number A is this equation, T in degree Fahrenheit, because we want to know what is the temperature in degree Fahrenheit, is equal to 9/5 temperature in degree Celsius plus 32. Okay, so 9/5, and temperature in degree Celsius is 20 degrees Celsius, 32. So this is the first term is this is 436 plus 32. So it's basically 68. So 68 degree Fahrenheit. Okay. And number B is basically very simple. T in Kelvin is equal to T in degree Celsius plus 273. Okay, so normally it's 273.15. Let's ignore the decimal places. So it is 20 degrees Celsius plus 273. So it is 293 Kelvin. So the room temperature in Kelvin is 293 Kelvin. Okay. All right. Not too bad. All right, now the next one. So this is about linear expansion. Okay. Okay, so we are given the length, okay, of something. Okay, so here the San Francisco's Golden Gate Bridge. Okay, and the temperature change. Okay, so it normally changes from negative 15 degree to positive 40 degrees Celsius. Okay, and then it says that the bridge is made of steel, and then the linear expansion coefficient for steel is this. So with this, we have to calculate what is the change in. So we have to calculate what is the change in length. Okay. All right. So we learned that delta L, the change in length, is equal to this alpha L0 delta T. Okay, so alpha, L0, and delta T all are given here. Okay, so L0 is 1275 meter. Alpha is also given 12 times 10 to the power minus 6, but delta T is not given directly. So let's first calculate delta T. So delta T is final temperature minus initial temperature. Here final temperature is 40 degrees Celsius and initial temperature is minus 15 degrees Celsius. Okay, so this minus is very important. Here you see this minus and this minus becomes plus. So it is basically 40 degrees Celsius plus 15 degrees Celsius. Altogether, it is 55 degrees Celsius. Okay, so many students make mistake here. Okay, they just ignore this negative sign and get 25 degrees Celsius, which is wrong. Okay, so now if I plug all the value here, we get something like this: 12 times 10 to the power minus 6 degrees Celsius. L0 is 1275 meters, and then delta T is 55 degrees Celsius. Okay, so if you plug these three values in your calculator correctly and multiply, you should get 0.84 meter. Okay, so that means between winter and summer, when the temperature changes from minus 15 degrees Celsius to 40 degrees Celsius, the length of the bridge changed by 0.84 meter, is approximately 1 meter. Okay, all right. Next, again, it is the linear expansion. So here we are given an iron ring whose diameter is this. Okay, so let me change the color. Okay, so iron ring whose diameter is 1 meter. It is basically the diameter. Okay, and it says that okay, which is this is to be shrunk on a pulley, which is so pulley, we have another pulley and its diameter is 1.005 meters. Okay, so we have one ring that's diameter is 1 meter and the pulley's diameter is 1.005 meters. Okay. Okay, now the temperature of the ring is 10 degrees Celsius. Initial temperature. Okay, we have to find the final temperature. Okay, so final temperature we have to determine. Okay, so that it will just slip on the circumference of the pulley. Okay, and both, let's say both are made of a steel or iron. Okay, the iron and steel has both have the coefficient of linear expansion, and that is equal to the same coefficient of linear expansion, and that is equal to 12 times 10 to the power minus 6. Okay, now we have to calculate the final temperature. Okay, so let's see how to calculate. So again, the starting point is this equation. Delta L is equal to alpha, the initial temperature, initial length, and the delta T. Okay, delta T. Okay, so this is the initial, the equation. So here, let's try to understand, pictorially. Okay, so let's say this is the ring, okay, whose diameter is 1 meter, and we have a pulley. Okay, so let's say this is the pulley, which is little bit higher, whose diameter is little bit higher than the ring. Okay, and we have to be the ring is to be shrunk on this pulley. Okay, so because it is 1 meter, okay, normally it cannot fit on 1.05 meter, right? So what we have to do, we have to make it at least 1 point. We have to make, we have to expand the ring so that its diameter is 1.050 meter, and then we can put it on the pulley, right? So what we have to do here is we have to change the diameter of the ring, okay, by this amount. We have to change the diameter of the ring by this amount. Okay, so this is basically okay. So that means we have to change delta. We have to make the delta L, which is equal to 0.05 meter. Okay, so to increase the length or the diameter of this ring by this amount, 0.005 meter, what temperature we basically need? Okay, so here we already know that this left hand side is 0.005 meter, and the ring is iron ring. So alpha is 12 times 10 to the power minus 6 degrees Celsius. The diameter for the ring is 1 meter. So this is 1 meter. Okay. Delta T, let's first calculate delta T. So delta T would be, so let's solve this for delta T. It would be, and in the denominator we have 12 times 10 to the power minus 6 degrees Celsius, 1 meter, and that is equal to, I got something like this, 416.7 degrees Celsius. Okay. So delta T is this, and delta T is what? Delta T is the final temperature minus initial temperature, right? And that is equal to this degrees Celsius. We have to calculate the final temperature, and that is equal to T0 plus 416.7 degrees Celsius. And T0 is given to 10 degrees Celsius. So 10 plus 416 is equal to 426.7 degrees Celsius. So the ring needs to be heated up to 426.7 degrees Celsius. If you want to fit this ring on the pulley, we have to change the temperature, we have to increase the temperature, and that final temperature is 426.7 degrees Celsius. Okay. All right. This one is a volume expansion problem. So let's see what we are given and what we have to calculate. Okay. So we are given that the volume. Okay. So we have given some initial volume. Okay. So this is initial volume. Okay. So this is initial volume. Okay. So we'll be using liter, not the gallon. Okay. So yeah. So, and it's made of steel. Okay. So we have 60-gallon steel gasoline tank and is full of gas. Okay. So inside 60-gallon tank, we have 60 gallon of gasoline. Sorry, 60 liter of gasoline. Okay. Now here we have two objects. One is the tank, another is the gas. Okay. So both can expand or contract with temperature. Okay. So the initial temperature is 15 degrees Celsius. Final temperature is 30 degrees Celsius, 35 degrees Celsius. Okay. The coefficient of volume expansion for iron is this, and for gasoline is this. Okay, so that's the given information. And what we have to calculate? We have to calculate how much gasoline has spilled by the time when the temperature is changed from 15 degrees Celsius to 35 degrees Celsius. Okay. All right, so let's see. So here, basically, we have to solve the volume expansion, okay, both for the tank, the steel tank, and for the gasoline. So we basically have to determine delta V first for the tank and then for the gasoline. And then we have to determine how much gas is basically spilled when the temperature is changed by 20 degrees Celsius. Okay, so for both the gasoline tank and the gasoline, the initial volume, I mean the original volume is 60 liter. Okay, for both, delta T is the final temperature minus initial temperature, and that is equal to 35 degrees Celsius. I mean 35 degrees Celsius minus 15 degrees Celsius, and that is equal to 20 degrees Celsius. Okay. Now for tank. tank, delta V equal to beta V0 delta T, and that is equal to, for tank, it is 35 times 10 to the power minus 6 degrees Celsius, 60 liter, and then temperature is 20 degrees Celsius. So the change in volume for the tank is this. So I got something like this. And the same thing for the gas, delta V is equal to beta V0 delta T. Now the only difference is the beta. Beta for the gas is this. And then 60 liter tank means the gasoline's original volume is also 60 liter, and the temperature is, change in temperature is also 20 degrees Celsius. So this gives me 1.14 liter. Okay, so when the temperature changed from 15 degrees Celsius to 35 degrees Celsius, the tank is expanded by 0.0420 liter. On the other hand, gas expand by 1.14 liter, okay, which is much higher than the tank. So of course, there will be some gas spilled out. Okay, then how much will be spilled out? That will be 1.14 liter minus 0.0420 liter, which is equal to 1.10 liter. So this mass gas will be spilled out from the tank. Okay, because the change in volume for the gas is higher than the change in the volume of the tank. Okay. All right. The next one is about the thermal stress. Okay. All right. So what we are given? We are given the length. Okay, so the length is this, and it is a concrete slab. Okay. Now we have to calculate the stress, but yeah, but first let's see what are the other given information. So the temperature, it says the temperature is increases by 30 degrees Celsius. So it means that the delta T is 30 degrees Celsius. Okay. There are some initial temperature and there are some final, I mean, there is some initial and final temperature, but we don't know what is the initial and final, but it tells that the change in temperature, delta T, is 30 degrees Celsius. Okay. And it also given us the coefficient, I mean, the linear expansion coefficient for the concrete and the Young's modulus for the concrete, or the elastic modulus. Okay. And we have to calculate that how much stress a slab would produce if the temperature, okay, so we have to calculate basically the stress. Okay. Now remember that we already derived the equation for thermal stress, and it was something like this. F over A, that is the thermal stress, and the equation was elastic modulus, or the Young's modulus, times the alpha times delta T. Okay, and the good thing is everything on the right hand side are known. So Young's modulus, or the elastic modulus, is 20 times 10 to the power 9 Newton per meter square. Alpha is 12 times 10 to the power minus 6 per degree Celsius, and delta T is 30 degrees Celsius. So when you plug all together everything, it gives you something like this: 7.20 times 10 to the power 6 Newton per meter square. So thermal stress for this problem, for the 12.5 meter long concrete slab, is 7.20 times 10 to the power 6 Newton per meter square. Okay. All right. Next problem. All right, so we are given the volume. Okay, no, I mean we have to calculate the volume, and given that the we have calculate the volume given that we have 1 mole of any gas, okay, and assuming that it behaves an ideal gas, and STP. So you know that here it says about STP. Okay, so although it didn't give you the number, but by STP you should know that what is the pressure, what is the temperature. Okay, and number B, we are given the volume. So this is the volume, uh, and again we have given it in STP. And for the first one, we have to determine the volume, and for the second one, we have to determine the moles. Okay. All right. So let's see. For number A, okay, but before I solve, let me write down what STP means. Okay, so T means 273 Kelvin. Okay, and P means 1.013 times 10 to the power 5 Newton per meter square. So STP means this pressure and this temperature. Okay, and remember that whenever we in any equation, whenever we have T, we have to plug the value in Kelvin. So if it is delta T, then we can use either Kelvin or degree Celsius, it doesn't matter. But whenever we have T in an equation, okay, then it must be in Kelvin. Okay. All right. So how to solve this problem? So here, you know, T and P, you have to calculate V. Okay. And we also know the mole. Okay, so I think we can use this equation, PV equal to nRT. Okay, so we have to calculate volume. So if I solve it for volume, it is something like this, nRT over P. Okay, so what is N? N is 1 mole. Okay, for number 1 it is 1 mole. R is a constant, so we should copy this number from the textbook, and this is this joule, mole, Kelvin, and T is 273 Kelvin. Okay, and P is this one, 1.013 times 10 to the power 5 Newton per meter square. Okay, so this is basically V. If you plug everything correctly, you should get something like this, 0.0224 meter cube. Okay, now you can convert it into liter, but yeah, that's fine. I mean, just keeping this is fine. Okay, meter cube is also basically the standard unit for volume, so this is fine. But if you want to convert it into liter, okay, it will be 22.4 liter. Okay, you use the conversion from meter cube to liter and check that whether you can get this. Okay, number B, here we have to calculate the number of mole, n. Okay, so you can again use the same equation, but now solve it for n. Okay, so if you solve this equation for n, you get something like this, PV over RT. Okay, so what is P? P is 1.013 times 10 to the power 5 Newton per meter square. V is, for the second one, V is 1 meter cube. Okay, what is R? R is constant. Again, it is 8.314 joule mole Kelvin and T is 273 Kelvin. So if you plug all this value correctly, you should get something like this, 44.6 mole. Okay. All right. Let's go to number 7. All right. So here we are given, okay, so here we have to calculate the number of moles in a bike tire with a volume. So volume is given. Okay, so we are basically going to use meter cube, not liter. Meter cube is the standard international unit. We are given the pressure. Okay, Pascal, PA is the pressure. Pascal and Newton per meter is Newton per meter square. Both are the standard international units. So pressure's unit is either Newton per meter square or Pascal, PA for Pascal. Okay, so both are standard international units. So it's okay just to keep as is for the pressure, and it also gives us the temperature. Okay, now we have to calculate the number of moles again for the last problem. Okay, again very similar to the last problem. Okay, we have to calculate the number of moles. Okay, all right, so let's try using the same thing. We can use the same equation. So PV equal to nRT. Okay, so if I solve this for n, we get PV over RT. Okay, so P is given, and that is equal to 7 times 10 to the power 5 Pascal or Newton per meter square is the same thing. V is given, and that is equal to 10 to the power minus 3 meter cube. R is this one. But T here, we have to be careful. Okay, it's given in degrees Celsius. So you know that because it is T in the equations, we have to convert it into Kelvin. So how to convert it into Kelvin? Okay, plus 273. So we have to add 273 to it. Okay, so that means the temperature here is 291 Kelvin. So whenever you have this kind of problem, make sure you convert temperature in Kelvin, not in degree Celsius. If you plug the value in degree Celsius, you get incorrect number. So the answer is 0.579 mole. Okay. All right. So two more problem. So this one says, suppose your bicycle tire is fully inflated with an absolute pressure okay, so absolute pressure is given here. And temperature, okay, again, make sure you change the temperature in Kelvin. Okay. Now, we are given this pressure and temperature for some state. Okay. For let's say for some state of the gas inside the bicycle tire, actually the air inside the bicycle tire, and let's consider that the state is 1. Okay, so this is the state 1. So the state in state 1, the pressure is this and temperature is this. Okay, now it asks us to find the pressure in state 2. Okay, so pressure in state 2 when the temperature has risen to 35 degrees Celsius. Okay, So in the state 2, we know the temperature, but we do not know the pressure. Okay. And it said that assume that there are no appreciable leaks on the change in volume. Okay. So that means we can assume that the volume in state 1 and volume in state 2 are the same. Okay. So to solve this problem, again, we are going to use the ideal gas law or the equation of state, but another form. So remember that we derive an equation something like this. Okay, so we are going to use this equation. Okay, so here the question already mentioned that okay, the volume is constant. Okay, so since the volume is constant, I mean there is no change in volume, so we can cancel the volume. Okay, so the equation is basically now very simple, right? P1 over T1 equal to P2 over T2, and we have to calculate basically P2, and if I solve this for P2, it will be T2 over T1 times P1. Okay, now before you plug the values here, make sure you change you convert the temperature in Kelvin. Okay, so 18 degrees Celsius means it is 291 Kelvin. Okay, and T2, the final temperature, 35 degree plus 273, and that is equal to 308 Kelvin. Okay, so make sure you change your temperature into Kelvin. So 308 Kelvin to 91 Kelvin, and pressure is 7 times 10 to the power 5 Pascal. So if you plug these values in your calculator, it should give you the pressure is equal to 7.41 times 10 to the power 5 Pascal. Okay. All right. And the last one is this one. So this is the last for the chapter. All right. So here we have to calculate the average kinetic energy given that the gas is at 20 degrees Celsius, means at room temperature. Okay. So here for any gas. Okay. And here it is for the nitrogen molecule. Okay, so for the first one is the first one is to calculate the average kinetic energy, and second one is the RMS speed, but for nitrogen molecule at room temperature. Okay, so we have to calculate first the average kinetic energy and then the RMS speed. Okay, so average kinetic energy for any gas, but then the RMS speed for nitrogen. Okay, so let's see. Number A. So temperature is in degrees Celsius. So 20 plus 273, it is 291 Kelvin. So let's first convert it into Kelvin. And then average kinetic energy, if you remember, the equation is something like this: 3 over 2 Boltzmann constant times the absolute temperature for any gas. Okay, so Boltzmann constant is 1.38 times 10 to the power minus 23 joule per Kelvin, and then absolute temperature is 291 Kelvin. Okay, so it is basically this. Okay. So the average kinetic energy of a gas at room temperature, or I mean at 20 degrees Celsius, is 6.07 times 10 to the power minus 21 joule. And number B, the RMS speed. So remember that the equation we derived for the RMS speed is something like this: 3 kT over m. So here m means the molecular mass, okay? And we have to determine the molecular mass of nitrogen, okay? So for nitrogen, the atomic number is 14, okay? So the mass of nitrogen molecule, okay, so it is the nitrogen atom, okay, and nitrogen molecule means we should have 2 nitrogen atom, okay. So this is I mean N2 means nitrogen molecule, so nitrogen molecule is 2 equal to 2 nitrogen atom, okay. So 2 times 14 gram, I mean 2 times 14 unit, I mean the atomic mass unit, so that is equal to 28 atomic mass unit, and 1 atomic mass unit is equal to 1.66 times 10 to the power minus 27 gram, I mean kilogram. Okay, so when you multiply this with the 28, you get the molecular mass for nitrogen, and I get something like this. Okay, so now you see that for number B, we know everything. So plug all this value here and then determine what is the RMS speed. Okay, so K is 1.38 times 10 to the power minus 23 joule per Kelvin. Temperature is 291 Kelvin, and the molecular mass is 4.65 times 10 to the power minus 26 kilogram. Okay, so you plug these values correctly, you should get something like this: 511 meter per second. Okay. All right, so this is the RMS speed for nitrogen molecule at room temperature. And this looks like the end of this chapter. Okay, so in the next lecture, I will be talking about the next chapter, chapter number 14.